Thank you. So hello everyone, my name is Michael. So I am from the Trinity Center for Asian Studies. But before taking my PhD here, I was affiliated in the University of the Philippines in Quezon City. And that's where most of my work on like speech technologies for Philippine languages happened. So I'm just going to like share with you the work that's been done by a research group on developing speech technology, speech and language technologies for under-researched languages using Philippine languages as a use case. So I'd be taking you through like our development decisions on how we created the tools and then how we use those tools for various applications in our country. So why did we do this in the first place? So well, it came about with trying to solve some key concerns or issues in the country. So the Philippines is home to 170, 180 languages. But the problem with that is even we have so many languages, there's not much presence, digital presence of these languages, which becomes a hindrance into like intellectualizing these languages. So most of the languages in the Philippines exist in the oral space, in informal spaces. But when you go to like formal settings like classrooms, offices, government offices, it's either you use Filipino, which is the national language of the Philippines, or English. And actually, I'd say in more formal settings, we actually use English more than Filipino. But we wanted to change that. So the government, I think in 2012 or 2013, put forth an education reform. So before 2012, we have the bilingual education policy, wherein students, young learners in the Philippines, would be taught using Filipino and English as mediums of instructions. And then if a need arises, teachers can use the mother tongue as an auxiliary language to facilitate communication of ideas. But it's not the medium of instruction. The idea here is they want to promote a generation of Filipinos that are proficient in those two languages. So that was the policy before, and then they changed it into a mother tongue-based multilingual education system. So this gives a more prominent focus to the mother tongue of the Philippines. And I think it started with like 12 languages in its first pilot in 2012. And what happens now is that on the first 3 years of primary education, teachers can now use the mother tongue as the medium of instruction. We introduce Filipino and English on the side, like they have like classes, but the medium of instruction is still the mother tongue. And then we slowly introduce Filipino and English as mediums of instructions in the latter part of primary school and in high school. Okay. The problem with that is when it was implemented, there are no teaching materials and there's no training on how to implement this mother tongue-based education. And then couple that with our issues in education when we have like a large student to teacher ratio in the classroom, and we don't even have like a 1:1 ratio for like textbooks and students. So it's kind of like a challenge to kind of like use mother tongue to converse, exchange ideas when your material is in a different language. So another reason for doing speech and language technology is what happens to the graduates of our education system. Like, how can they be ensure that they will get jobs? So also in that time, around early 2010s, it was the BPO boom, business process outsourcing boom in the Philippines. So if you know, like call center agencies, any outsourcing companies, the Philippines would be one of your go-to destinations. And now you probably might have heard that, oh, Filipinos are good in English because of like how we were educated. But the thing is, in reality, we might have a good grasp of the language, but to get to a point wherein we are hireable, that's a different story. So when the BPO sector of the economic sector was reporting on the percentage of hiring in the Philippines, it's actually less than 10%. So it's not even enough to meet the demands of that sector. So there is also a need to kind of like, how can we bump up the proficiency of Filipino graduates so that they would be hireable? So that's where our universities considered, why don't we use technology intervention to help address these challenges in the country. So our attempt to this was to propose a series of research programs, starting with the ISIP program. So ISIP stands for Interdisciplinary Signal Processing for Pinoys. Pinoys is this colloquial term to refer to the Filipinos. Signal processing because the proponent of the research program is from the engineering department, specifically the digital signal processing department of the university. But it also collaborates with experts from other fields, thus the interdisciplinary part. And the idea is to have this research program that has 3 different functions. So either your function would be to create digital databases for the different Philippine languages, or you either develop core technologies which will be used in different end user applications, or your project would be on the specific development of that application. So we have here on the first research program round, so we have 7 projects. So for the databases, we have the Bantay Wika, which I think I can roughly translate to like Language Watch. So this is a digitized collection of texts, Filipino texts from, I don't know, I think, if I'm not mistaken, since the time of like Spanish occupation up to present. So this big collection of digital texts, which will enable, for example, culturomics research, wherein you analyze trends or evolutions of like the culture of the local community through an analysis of the recorded text. And then for the spoken part, so we have the Philippine language database. So this is a collection of spoken recordings, both read and spontaneous, for 10 Philippine languages. So, and if you recall earlier, I said that the first rollout of the mother tongue-based multilingual education is piloted for 12 mother tongue languages. So 10 of those is part of the PLD research project. Now for the core technology, so that's where we kind of like branch out. So we have a partner university who's working on natural language processing. So they are in charge of like analyzing code switching in text. So if you have Filipino friends and they start talking in Filipino, you'd see, or you'd probably understand half of the conversation because we sprinkle a bit of Spanish words in there and a lot of like English words in there, and you'd think we're not speaking our own language, but that's actually Filipino in the wild. So one project aimed to like look at that and study that. And then the other 2 projects are speech to text and text to speech. We started first with Filipino, and it's just because of the nature of the research project. So funding programs, it comes with a deadline. So they just wanted to have like a proof of concept, and if that works, then they can expand to the other languages. Now, because of the primary aim to address issues in education and upping the proficiency of graduates in the Philippines, so that became the core focus of the other projects that are on the application side. So we have the Filipino and English essay grader from our NLP partners, and then for our side, we were tasked to develop this proficiency tool for the Philippine English language, which we termed Learning English Applications for Pinoy or LEAP. There's a lot of like acronyms here because our funding agencies wanted to have like a nice acronym for everything, which may be also the same in your case, but yeah. And then when that became like a success, so we went on to like push for other applications, again in the education sector. So to promote the digital presence of the Philippine languages, so one project focused on the feasibility of providing closed captioning services for Philippine media. So this again focuses on the 10 Philippine languages that were wherein corpora is collected from the PLD research project. And then we have writing tools for Filipinos. So we moved on from evaluating their work to actually helping the students while they're working on their written work. So, and here is a screenshot of like Grammatica. So just for a grammar checker, but like it also has like I don't know, like packages you can download for like LibreOffice and other like word processing software. And then where I personally worked on is Project One, which is like the reading tutor for young learners of Filipino. So the previous one, LEAP, was for adult learners of and then focusing on English. So I was focused on developing speech technologies for young learners of Filipino. And then there's also a parallel effort for Bangsamoro languages. So these are languages that are present and dominant in South Philippines. These are actually, many of these languages are considered lingua franca and were added to like the second rollout of the MTB-MLE policy, the mother tongue-based education policy. So this is a more of a complementary project wherein they tried to collect data for these languages and then create parallel educational tools. So I think they focus on education assessment for the first phase of their project. So when we did our research for all the free research programs, so the way we tackled the problem is dependent on like what was needed. So for example, the Philippine language databases, linguists have interest in using them for doing phonological analysis, comparison among languages, but the problem is you're collecting hundreds of hours of data for these languages but you have to annotate them. So how are you gonna do that? So there we considered, okay, can we do like a semi-automated approach to create, for example, phone level time-aligned transcriptions, and then that way we'd speed up the process from annotation to performing analysis. For the closed captioning project, so we don't have speech recognition technology for the Philippine languages at the time. So here we explored, okay, can we do like model adaptation and bootstrapping of existing speech recognition models so that we can develop maybe like a baseline system for our own languages. Now for the reading tutor, so a common problem in children's speech recognition is that if you just plug in like an adult, a speech recognition system that's trained on adult speech, it's not gonna work because the spectral properties of children's speech are highly variable and very much different from adult speech. So here we look at, okay, can we do like some feature transformation? And the more recent work was looking at like large model fine tuning, at the advent of like, self-supervised language models. So how can we use that to our advantage? So I presented this in like 3 different cases. And then the first case would be the one wherein we address the needs of our linguists. So our linguists were like, okay, we have the data now. We wanted to do some phonological analysis, but we cannot spend a lot of time and manpower producing time-aligned phone-level transcriptions for a language that has 200 hours of data, because that was our goal. Each language would have 200 hours of data. So how are we going to transform this read and spontaneous speech to something that they can be used for their language analysis? And on the other end, there's another project there that's about text-to-speech. And at the time, the most popular approach for speech synthesis or text-to-speech is concatenative synthesis. So concatenative synthesis means that you're actually using actual recordings of the speaker and then automatically finding a way to splice them together to produce synthetic speech. So this produces a very natural speech output, but the problem is that you're saving this huge chunk of recordings because you need all the exact examples or exemplars to produce the whatever output that you need. So phone level time aligned transcripts. So how do we do that? So we just look for like a classical approach, which we call force alignment, and then okay, let's see how we can work with that. So force alignment is very much related to speech recognition. And so if we know speech recognition, it's easy to understand force alignment. So for speech recognition, it's basically speech to text. So the task is identify what was spoken. Your input to your AI system would be a speech recording of unknown content, and the output would be hopefully a faithful text counterpart or text version of that recording. Now for force alignment, we naively call it like a simpler task because you actually have a copy of what was spoken. It can be words, it can be the list of phones that match the speech, but the problem is you don't know at which part of the recording a specific sound was spoken. So the task is to match the speech with the transcript. So your input is your speech and your transcript, and the output is just a time-aligned version of that transcript. So FA or force alignment in principle should provide us with the initial time-aligned phone level transcripts. So our approach was like, can be broken down into two phases. So the thing with force alignment is you need a model, which is the model would be like mathematical representations of the different sounds that exist in the language. But like nobody's developing any of those models for Philippines yet, so we were the first. So it's kind of like a chicken and egg thing. So what we did is we kind of like develop our own crude models for the language. And it's basically described by this block diagram. So our inputs, we start with word level transcripts because we have read speech. So we already have the transcript. We ask them to read it, so we have, matching speech and transcript data. So obviously we have the speech recordings. And then the key input for this approach would be your dictionary. So it's not the dictionary, it's specifically a pronunciation dictionary, wherein each entry is described by a sequence of sounds that make up the word. So for example, this is a subset, so for English words, so I have here call, so you have the K sound, the O sound, the L sound, and then SP stands for short pause. So just to kind of like provide information that, oh, maybe the speaker paused after this word, so there's an optional sound label there. Now you might be weirded out with the representations that are used for the different sounds. So this one specifically is using alphabet, which I think is like a military-inspired notation for the different sound representations, because at that time, so IPA, it doesn't really lend well for like programming before. So they kind of looked for a different naming system that would be easily processed by programming software. And then now it's there's Xampa, but then I think programming has advanced in a level that you can actually now directly use IPA to produce these pronunciation dictionaries. Okay, so once you have those three, so it's a two-step process for this first phase. So first you need to generate your phone level transcript preparation. So it's basically like looking up the words. Are they in the dictionary? What is the what is the phone sequence corresponding to that word, and then that will give you the phone level transcripts. Now, in cases where in other languages, for example, English, there might be multiple pronunciations for a language. So in this stage, it just picks at random, or maybe the first pronunciation. But luckily for Filipinos, we don't have that problem. So we have this saying in the Philippines, "Siyang sulat, siyang bigkas." You write how it is pronounced. So we basically have like a one-to-one mapping between the orthography and in the sound sequence. So once you have these phone level transcripts, you pair it with your speech recordings, and together with your pronunciation dictionary, you produce, you start to train your model. So this is done in an iterative fashion, wherein for each model, you inspect the time-aligned, automatically, the time-aligned transcripts, see if you can improve it, and then do another iteration, so on and so forth. And then what you end up with is an acoustic model. And as I've said earlier, an acoustic model in this case would be a statistical model, one for each sound that you declare to be present in your language. So for example, in this language, in English, so there would be an acoustic model for the short ah, for the EY sound, for the O sound, for the L sound. So they will each have their own statistical model, okay? And then once we have that, so that acoustic model that you generated in the first phase becomes part of your set of inputs now. And together with those other inputs, your word level dictionary and pronunciation dictionary and speech recordings, then you do your force alignment. And from there, based from the information that was kind of like summarized in your acoustic model, you generate your time-aligned phone level transcripts. So in this case, it worked for us because, as I said, so we write as you hear it, so it was easy for us to generate the pronunciation dictionary. So usually that's the bottleneck for like many languages. Sometimes the generation of that knowledge source is not that straightforward. But because we just play with like a very simple set of rules, we can just automate this, and the pronunciation dictionary becomes readily available. We can implement this. And then upon consultation with our linguists, so we had this crude and minimal phoneme inventory, which worked for them. There would be some cases wherein they would say like, oh, some speakers would have a different realization of a sound, but compared to like the general population or speakers that we have on our data set, that's very infrequent. So that's how we solve the case of like how to generate phone level time-aligned transcripts for the Philippine languages. Next would be, okay, so that's for language or linguistic analysis. How about developing the core technologies as part of the research program? So in this case, so we look at how are we going to adapt existing models for speech recognition. So again, we start with the database from the Philippine language database, and then how are we going to leverage that to generate speech recognition systems for the 10 Philippine languages, and then use that for closed captioning. So this is like a sample input, wherein, so this is the video. It's not that visible, but that should be the transcript, and then the start and the end time, but like that will be displayed here as well. And then, so one of the languages, actually, I forgot to say for the PLD is actually Philippine English, because when we were trying to develop this English speech recognition system to train Filipinos to better speak English, it wouldn't accept the Philippine accent. And so we had to like exaggerate how we perceive US American English sound like, and then for some reason that works, but like it becomes unnatural, and it doesn't work for like when you're doing conversational setups. So we had to train our own speech recognition system that's tuned to like the Philippine English accent. So how do we do that? So our approach here is in cross-lingual bootstrapping. So So basically, the idea here is if you have an acoustic model from a different but related language that already exists, why don't you use that as a preliminary base model for your own language, and then from there, do an iterative training to produce the models that's specific for the language that you're trying to develop. So in this example, so I think here the goal is to generate a speech recognition system for French. So in this specific implementation, what they use is Italian. I'm not familiar if they're related, or I'm approaching this from a very engineering perspective, so I leave that to you if that makes sense. And then so what they did is, okay, at the start of developing this speech recognition system, we would need time-by-line transcripts. So let's just use the Italian model for that, and they did that. And then they did an iterative training of their own French models. And then from that iterative process, ideally this should produce a robust set of like French models for speech recognition in that language. So for Filipino ASR, we were partnering with somebody from Carnegie Mellon, and they have a very robust and kind of like mature technology for US American English. So that was our base. And that was the one that we used to develop our own Filipino ASR. Now, there's a lot of like things to consider there. Like, for example, in the phoneme inventory, they would have like a very wider inventory compared to like any of the Philippine languages that we're considering in our work. So there were like some decisions there wherein statistical models for phones that kind of like sound alike in our perspective, we kind of collapse it to one or kind of like get rid of them. And some are based from like an analysis of like, for example, Philippine English. So our observation, for example, of Philippine English is that we don't do well with distinguishing long and short vowels when we're trying to speak. Like maybe in read speech we do, but like in spontaneous speech, that goes out the window just to get through with like, you know, trying to make our point or like, you know, express our thoughts. So sometimes those differences disappear. So we kind of make decisions based on that. So even for the Philippine English ASR, we use the USA English acoustic models for our basis. So when we did that, so we started very poorly. So we have our base model. It was operating at a word error rate of 30%, which wasn't bad at the time. And then we thought it was a pretty stable system because when we tested it on a different set, so this is another set of recordings that's not seen by the model. The results were comparable, but as we tried different techniques, so it improved to a state wherein, okay, maybe we can deploy this in our applications. So just for a bit of context, this is a bit technical, but like, for example, context independent means your statistical models for your phonemes, you assume that they're not influenced by the neighboring phones, which I think we know is not true. But that's a very simple way, although crude way, but it's a simple way to get you a working speech recognition system. And then when we try to incorporate context wherein, okay, if say a phone was pronounced by a beginning B and a final T, that's a separate model compared to the same phone may be pronounced with a beginning S and then an ending T, for example, that's a different model. So when we're able to do that, although that requires more data, so we were able to massively improve the performance of the system. So kind of like almost reducing the word error rate into half. We tried other things as well. So this one, VTLN, is like a speaker normalization approach, wherein we try to like meddle with the spectral properties of the input speech before feeding it to the speech recognition system. That didn't seem to have a lot of improvement. We also tried to see if manual corrections would make an improvement. Now, in this context, this is more of like a baseline study. So because the data that we were getting, so we also have spontaneous speech. So sometimes when our speakers would be answering a question, they would mix in their Spanish, they would mix in their English, and then our pronunciation dictionary sometimes won't have like models for those English or loan words, and and of course the system would be forced to map it to whatever word that it knows, and so we tried to kind of like correct that, but like the performance was like marginal in terms of improvement. Yeah. So this works, and then I think we are happy that it's not just us that's implementing this approach. And I think if you're doing this approach, your things to consider would just be, you know, the phone inventory mapping across languages. So that's why it's important that your seed model would be a related language to the one that you're trying to develop. And then there's a bit of like hand-holding in this process. So you have to like check the intermediate outputs of your system and see if like during the iterative model training process, does your system improve its performance. So with that, we're able to like, okay, we're now able to like produce speech recognition systems for our Philippine languages, but that's for adults. And now when we move to our next research phases and we were dealing with children's speech, so as I've said before, it wasn't working. But like the goal was to use these speech technologies in an educational system, in an educational setting, and you can't afford to have your you know, technology, underlying technology make a lot of mistakes. So just to illustrate, this is how we envisioned using speech recognition specifically for our reading shooter program. So this is Tanglaw, which is a word for like torch or light, and this is our reading shooter for the Filipino language. Let's see it works. So yeah, so we deployed that in the schools. So the idea would be to use Tanglaw as kind of like a supplement to regular classroom instruction. So for example, there would be students who would be falling behind in their fluency and reading comprehension skills. So they would set aside time outside normal classroom instruction and then use the software. And usually they would do this in like a separate room, or if it's a fancier school, they would have like a computer lab, and they would use the software. So that software would have like opportunities to practice skills and fluency. So for example, here wherein they read these phrases, and then the reading tutor would be in charge of like finding out which items were read incorrectly, and then provide appropriate feedback when necessary. So for example, in this case, the student, for example, misread the phrase "ilaw sa kisame," which is like light on the ceiling. There you go, Philippine English. And so we try to like connect the text with an image, and hopefully that would like register better and deeper to the student. And of course, this would have an accompanying model pronunciation, and then that the student can listen to, and then hopefully next time they try the exercise, they perform better. Now, so that's the goal. No, but to work, we need to address this fundamental problem with speech recognition. So most of the features in speech recognition rely on representations of the spectral contents, which means like we look at the frequency, find a numerical representation based from that that frequency perspective, and then generate the features that you would feed for your speech recognition. But an analysis of like the spectral content of children's speech shows that it's highly variable. It's varying across age, varying across gender, and also varies from one child to another. So this is just like an illustration of that variation, wherein when Potamianos and Narayanan, they mapped their vowel spaces for children of different ages. So they saw that it occupies different regions. And then when they compared it to like the adult vowel spaces, so there's a trend that it kind of like approaches the adult vowel space as they grow older. Okay, so this has been explained as, because of the vocal tract length, it changes as the child grows older. So that shifts the form and structure or just changes the spectral content altogether. So that's why adult trained models, they perform poorly. Now, one might say, okay, why don't you just create something from scratch? Well, the problem is, if there's high variability in the data, then you need more to generate better models. So that's the thing. And it's not like you can have a student sit down for 1 hour, read a lot of passages, and then they will not be kicking and screaming. I mean, the novelty of facing a computer or a software wears off after the first and the second session. So we have to be creative with how do we make this children's speech recognition a reality. So our approach would be feature transformation, and here I'd be discussing one, which is about frequency warping. So because the changes are happening in the spectral domain, so why don't we kind of undo the changes in the frequency warping, or find a complementary changes that will undo those initial variation in the spectral domain. So from a big picture perspective, so what happens is before you generate your mathematical or numerical representations that you will feed for your speech recognition system, or before you train your model, you have an intermediate approach, which we call frequency warping. So your speech recording gets warped in the frequency domain, that changes the spectral content, and then you do your usual feature extraction, and then you can proceed with your modeling and decoding. There are other approaches wherein you actually, for example, change the model as you try to process and input children's speech data. But we chose this approach because this has the least impact on an existing system. And so remember, we're using this inside a reading tutor. So if we're changing the model every time it's running, so that will introduce latency, and so the student will be sitting there waiting for this computer to finish running, and they might get bored. And also we set up the software such that it would receive continuous input from the child, and then if the input is very long, it's reading several words or even a story, so that will take a longer time to process that, and so we need something that kind of has a minimal impact on the existing model, makes the changes on the feature level, and that way we don't encounter that much latency. So this frequency warping has been adopted by other researchers as well, and they've investigated this on for example different sounds, what do you do when you compare, for example, the unmodified sounds with the adult speech, or versus the modified sound or frequency warp sound with the adult speech, and they saw a remarkable reduction in the distances of the features that you produce when you did warping versus not doing any warping at all. The catch with this approach is it's also still variable, because again, children's speech is variable, so you apply different warping intensities, as I call it, depending on the gender of of the speaker and then the age of the speaker. So this scaling factor must be estimated, and you can estimate this like prior to implementing the system. Maybe you have a set of like factors that, okay, if the child is like 5 years old, this would be the amount of warping that must be done, or you can also do it on the fly. So what we did was, so we were ambitious, so we did that. And what happened was we introduced this exercise, and we framed it as like a primary exercise, just so you could get the hang of like using the software. So they just like read a passage, and they kind of, but like they already know, they're tech savvy and whatever, so they already know how to use the software. But we kind of need the data to estimate this warping factor. So that's what we did. And so for the next interactions with the underlying technology, so we just use that information. So just to show you how it works on the fly, so it's basically
aso, ulan, lapis, kabayo, maliit, gagamba, kaibigan, elepante, merienda.
So that's some volunteer reading a list of words, and then our system. Now this is a more verbose demo, because we needed to show the funding agency that it works so that we get more money. So, but in reality, it's more of like the machine talking to another machine, because this is part of like a sequence of processes to determine where the reading errors are. So there. So sorry, So actually, I should have shown the reference, but basically, the student misread the word daga, which is rat. He just said ga, which I don't know why. That's easy. And then the reading tutor would say, okay, you're first level. So now it's a bit harsh, because, like, if you think about it, he actually pronounced all the words correctly. But we were consulting with this education expert, and she was like, no, if the student makes a mistake, so that's the starting level of the student. So I'm like, okay. So anyhow, so that's how it ran. So I'm not sure if it's noticeable here, but like we also feed with the input recording the warping factor. So that our speech recognition system would know that, oh, okay, I need to perform some frequency-based transformation before I perform my feature extraction, before I figure out what words were spoken by the child. So we did a couple of like tests as well. So this is on a small vocabulary system comprised of like several different stories that the students were tasked to read. So here we have like 3 different models. So we did try like creating a children's speech recognition system from children's speech data, but even with their adaptation techniques. So VTLN is a frequency warping method. So we have speaker adaptive training as well. So it's same banana, just a different approach to transforming the features. So we still get like more than half in terms of the word error rate. And then what's funny was like when we did that when we test the same set of recordings with adult speech, even without performing some sort of like feature transformation, it has improved quite a lot, although not at a rate that we're comfortable to release in the reading tutor. And the reason here is this adult acoustic model is based from the Philippine language database data, which is like significantly more data compared to the one that we're working with children's speech. So that's playing a role in here. But when we perform our feature transformation methods with the adult model, so that dropped the word error rate into like a figure that we're kind of like, okay, we can interface this with the reading tutor. We compared that with other research, and so in this case, it's a different trend, but only because they have comparable training data. But yeah, speaker normalization or frequency warping gives you improvements in the word error rate. So that's like some of the cases that we encountered in developing speech and language technologies for Philippine languages. Many of them are classical approaches. So I guess the natural question would be, what now? So like, where do these classical techniques reside in the era of foundation models? So are they still relevant? And has this affected the trajectory of our research for developing these technological tools for Philippine languages? So let's go over them one by one, like for example, force alignment. So I think, like personally, what happened there is that it's just more accessible now. So force alignment is still a popular approach for generating your phone level time aligned transcripts. So before, you need to like commit yourselves to like a specific speech recognition toolkit, develop the pipeline yourself, and then from there you would generate this system. Now you have like tools like the Montreal Force Aligner with like and it comes with like pre-trained models for different languages. And that lowers the barrier to entry. It even has the G2P model. So G2P stands for grapheme to phoneme, which takes care of the problem of how do we produce this pronunciation dictionary. So of course, again, it depends on like the appetite of the research community for that specific language, if they would develop these models. So usually the more widely used languages would have these tools already. So that's why sometimes pre-trained acoustic and G2P models, although increasingly available, is still like an active avenue for research and development. So, and as I said, there are these core challenges that remain for low resource settings. But there are actually other interesting research even in this space. So I saw just one person who's like developing this multilingual model for generating phone level time aligned transcriptions. And the idea is the output is not like phonemes for a specific language, but like in the entire IPA. Now I think it's in infancy. He just started the feasibility study. Oh, can I just generate this model? But this person is working towards language agnostic alignment, which is good. And I hope he does it because I need it. What about speech recognition? So there are modern experiments that we did for Philippine languages. So for example, one of our colleagues meddled with like transformer models using data that he collected in the wild. So specifically like YouTube videos. Now the problem with that is they don't have reliable transcripts. So what he did was he used the classical models that we have to produce this weakly labeled Filipino data, and then couple that with open source training recipes like in Caldi or like the models from Hugging Face. So we're able to create this system. So actually his system here is the F7X transducer, and he benchmarked this with existing systems out there and against different data sets. So FLIRS, if I'm not mistaken, is read speech relatively clean. Babel is the opposite. Crowdsource, very noisy, because if I'm not mistaken, the way they did it's like, oh, can you just record something on your phones and and then wherever they are, they just record. And so whatever noise conditions are present at that time, that gets recorded as well. So that's kind of like the other end of this testing scenario. And then material, I think, is clean speech as well, but I'm not sure if it's read or spontaneous. And so we can see that the performance is variable, specifically for Babel, which is like very noisy. So there's still like room to improve. But when we compare that with like other efforts produced by research groups outside our group, so it can hold its own. So we're happy with that. And then, but the next step would be to how to replicate this success for the other Philippine languages that we have at the moment. For children's speech, so we also tried to move from classical to SSL. So not me, but like the next phase of research that went after me, they explored self-supervised language models for Filipino and English ASR dealing with children's speech. And so there's still a bit of challenge there because the fine-tuning data required is still relatively large to what we have at the moment. So that's still like a bottleneck for us. But in terms of like techniques, so like that frequency warping technique that I mentioned before, I was surprised that it's also still relevant in current research. So because they still have the same problem, whatever your model is, if it's trained on adult speech, it's not gonna work straight for like children's speech. So now they're combining this frequency warping, except you have a different base model, and so now they're doing their baseline experiment. So I think this work by Scharenborg, so which I think is like the previous chair of interspeech, so they were working on like different languages like Dutch and Mandarin. So they have like promising baseline results. So but that's an active research right there. And that's the end of my talk. If you have any questions, I hope you were delighted by that. Thank you very much.
So this is the Digital Linguistics Pre-Matted Talk Series. Today is our second talk of the talk series. We are still at Trinity College Dublin right now, and the talk today is by Michael Bayona, Speech Technologies for Under-Resourced Languages, from Development to Application. The floor is yours. Thank you.
Yeah, so I'm Nathan Hill, and I'm here at Trinity College Dublin. I'm one of the participants, along with Jessica and Mathis, in this year's Erasmus Plus project. And I will just pass things over to Michael Bayona, who is just finishing his PhD here at Trinity College Dublin, and then is starting also a postdoc on a ERC project where the PI is Tim Bott, that will work on the endangered languages of Bhutan, specifically Gongduk and Monpa. But today he will probably be talking about Filipino and languages of the Philippines. So I will turn it over to him.